core to cloud. And here, this page is our online textbook that all about circuits.com. And if you click on education and then textbooks, volume 1, and then we scroll down, right? So far we finished chapter 1, 2, 3, 4, 5, 6, and 7. And the other chapters over here, even though we did not open this chapter and cover word by words, but we have seen the meters. And the meters appear on homework 1, homework 2, even test 1, such as the symbols. The symbols for the first meter is called the voltmeter. It looks like that symbol is not here. It's a circle with a V. That's a voltmeter. It's a device that measures how much voltage drops on an element, such as this 250 mega ohm resistor. We have also seen a meter. It has a circle with a letter A inside. That is called the ammeter, such as the next page. Here, we're not going to spend lots of time on this chapter because they just too much information, such as how to design this meter. We are not interested in designing, we are interested in how to use it. Such as here, a circle with letter A. This is a ammeter. Ammeter is a meter that measures ampere, which is current. And then besides voltmeter and ammeter, there are other meters. We're gonna spend remaining time and then explore the remaining meters. But today, our goal for today is not to cover this chapter. It's a very easy chapter. However, we're gonna spend our time finish another chapter that is called the capacitor. Here. This is chapter 12. And then between the previous chapter that we covered, chapter 7 to 12, there are some other chapters, but we are going to skip them. They are either just too much information or they are irrelevant, such as pH measurement. This is really not important to us. Even the next level, the level after next level, classes never mentioned measuring pH. Thermocouples, no. Taco generators, nah, that's just too much out of scope for the class. And here, even though they are important for electronics or electrical engineering, but they are just too much for our class. Such as mesh current method, Milam theorem, superposition. This is very math intensive. To solve a question, we need 2 pages of calculations. Just too much. That doesn't apply. That's the reason we skip these chapters. However, the next one is also in the curriculum, important. That's capacitor chapter. Today we're going to cover this. Okay. Any questions before we begin the capacitor chapter? Okay, let me switch the screen to the PowerPoint. So this is chapter 12. Chapter 12, it is about the second important electronic device in our class. And in most classes, that is the capacitor. So capacitor is a device that stores charges, store electrons. And in this chapter, we are going to cover following sessions. Session 1, 7.12.1 is called electric field or electric fields and the capacitance. And then the second session is called the applications of capacitor. Session 3 is different types, different categories of capacitors. We have capacitors made of using different materials. And then session 4, the factors that affect capacitance. And then the last session, series and the parallel ways to connect capacitors. So let's start with session 1. So first, we need to know what is a capacitor. Capacitor is just an electronic device, like a container, contains or stores charges, stores electrons. Once we put electrons inside, it stays there unless or until we dump the electrons, which means we let it discharge. So capacitance in the simplest form, the capacitor is the electric device. The simplest capacitor is made of 2 parallel plates. That's the simplest one. And then all other kinds of capacitors are made using the same principle. There must be 2 different parallel plates, 2 different layers parallel to each other. They can rolling into like cylindrical shape or like a rod, but the layers have to be parallel to each other. They cannot touch each other. So this is here is the basic principle for designing capacitor. There must be like parallel plates. These plates, each one is a conductor. However, the 2 plates cannot touch each other. If the 2 conducting plates touch together, electrons will flow through it. So the 2 parallel plates or conductor plates, they are separated by a distance. Between the distance, between the plates, we can put air, we can put vacuum, or we can put some insulating material. And this material has a special name called a dielectric. So let's use a picture to illustrate it. Here we have 2 parallel plates. Each plate has a like rectangular or square shape. In this case, 2 plates are parallel to each other. Between the plates is air or vacuum. So this construct the simplest, the easiest, the cheapest capacitor. Say double plate capacitor, and then each plate is such as metal, or it's made of copper, any kind of conductors. And then here, as you can see, this is one plate, conducting plates. This is another one, conducting plate. And those cylinders are just wires. In reality, the wire is not that thick. Here, just exaggerate. The wire in general not important. The plates with the material inserted between the plates, that is called the, together is the capacitor. So let's put this aside. And then here we get a real capacitor. This one is called electrolytic capacitor. It's one kind, one big category, one popular. Well, I think this is the most popular capacitor. It's called electrolytic. The capacitor using electronic devices use this kind of capacitor. Capacitor using circuit board. Most of them are this kind of electrolytic. The symbol, there are more than one symbol. This is the symbol, the simplest symbol, the general symbol. The symbol represents almost all kinds of capacitor. And then this symbol represents or shows capacitor with polarity, especially this one. This electrolytic capacitor has polarity, which means the way to connect it to the circuit is important. The orientation is important. One leg, one side connects to the positive voltage or a higher voltage in the circuit. And the other leg connects to the lower voltage. Sometimes negative, it doesn't need to be negative voltage, it's just lower voltage. The voltage is lower than the other side. And here is the electrolytic capacitor. And if you look closer, we're gonna look at this again with a better picture. We can quickly preview here. This one capacitor, electrolytic capacitor, one side has a ribbon, or has a strip, or a stripe here. And then on the top, there is a bar. This bar is negative sign. So which means the legs connect to this side is the negative side, the negative leg. So the other side, most of the time is longer leg that connects to the higher voltage, the positive or higher voltage. The other side, the short leg connects to the negative or lower voltage in the circuit. And then the side with the curve connects to the negative voltage. And let's see. Now we just look at this one. It has a name. It's called parallel plate capacitor. This kind of structure, this kind of design, this kind of capacitor is called parallel plate capacitor. It is the simplest capacitor we can make. Any questions so far? Okay, cool. Again, the material we put inside is called dielectric. Very soon we're going to see the dielectric material. Oh, there, yeah, here. Now we're going to put some materials embedded, and these are insulating material, insulators. And this is called dielectric. Sometimes we call it dielectric material, but in short, we can simply call it dielectric. And there are plenty of materials we can choose. And not everything, not every material, but plenty of them, such as glass or wax, oil. They are all insulators, and they can all be dielectric materials, or just dielectric. But now let's do some analysis, because after analysis, we're going to come up with one important formula, the formula for double plate capacitor. As long as we know those things, those quantities, those factors, we can figure out the capacitance, which means how large this capacitor is. So here we get a double plate capacitor, and we put that in a circuit. The circuit has one open switch and then a source, a DC source here called VS, where S stands for source. Well, now, let's just use this symbol easier, 2D. Right? That one is 3D, now we use 2D. So this is the initial state before we start the experiment. But now, let's start the experiment. So now experiment begins. The switch closed. Oh, now before that, before closing the switch, let's say here are the protons and the electrons floating inside the plates. They are inside the plates, floating. They don't move a lot. I mean, they don't move very fast. They just float in the region, but slowly. It doesn't travel too far. How about now? We close the switch. Close it. As soon as we close the switch, the electrons start to flow, right? Start flowing out from the negative terminal of the battery. And then more electrons floating out. As the time passes by, more electrons floating out from the negative terminal of the battery. Okay, let me speed this up. Okay, so as you can see, electrons are continue flowing, and then now enter one plate. The plate is kind of empty, where it's not saturated. It's empty, so it has space to have more electrons to enter. As you can see, yes. However, until certain state, until certain time, the capacitor, the plate is saturated. There's no more space. It cannot accept more electrons. And at that moment, no more electrons can enter. Those electrons are just live in the wires. And then here, if you look at one plate, it starts to reorient it. It starts to, how to say, it starts to, reorient it. and then all the electrons are lined up on one side. Oh, I think my PowerPoint freeze. Just give me 1 second. Just too many slides here, 190 slides. So my computer freezed. Just need 10 seconds for this to be rephrased or released. Okay, now it's good. So as you can see, all these electrons line up. They occupy one side of the plate, and the protons also line up, occupies the other side of the plate. The electrons on this plate repels the electrons on the other plate. Right? Same kind of charges, they repel each other. And at the same time, these electrons attract the protons on the other side, in the plate on the other side, in the other plate. So we can draw this arrow, and the arrows means this proton and the electrons, for all of them, they are attract to each other. They attract each other. They are holding hands. There's a binding force. There's some kind of force bind or connect these two plates. Imagine if we have a virtual hand. We don't use the real hands. We're gonna be electrocuted. But let's say we do have a virtual hand and virtually grab this plate and that plate and try to separate these plates apart. Right, one hand try to move this plate to the right. The left hand grab this plate and then pull this to the left. We can feel a force between the plates, which means it's hard for them to separate the plates because they are attracted to each other due to this proton and the dielectron for all of them. And at the same time, this proton and the dielectron, they are attracted to each other. So there's a attraction force. So this is the voltage. The arrows are, such as here, the arrows are called electric field. And then the force between the plate is called electric force. The electric force between the plates, this is the force to attract, to keep plates are not far away from each other. Any questions? Okay, cool. Well, let's see. Now we're gonna, oh, yes. Catholic, great. Questions? Oh, okay. And now we're gonna learn a new term. This term is, first, it's important. However, it's not too hard. When we cover resistance or resistance, we know resistor is a device. It can be a material, is some electronic components that resist current flow, resist electron flow. And then the capability of a resistor is called resistance. Similarly, similar to here, there is another device called a capacitor. Capacitor is a device that stores charges, store electrons. The capability of it, how much a capacitor can store things, how much the measurement, the capability is called capacitance. The capacitor with bigger capacitance can store lots of charges. A capacitor with little or small capacitance stores little charges. So capacitance is a measure of the ability or capability of capacitor to store charges. So that is called capacitance. The symbol of capacitance is uppercase C. This is uppercase. So that represents capacitance. In other words, the capacitance symbol is uppercase C. Uppercase C is the symbol of capacitance. The unit for capacitance is called farad or F. So if you get a capacitor and we look close at it, then we can see some number followed by F. Later we have examples. A single F, such as 1 farad, right? 1 farad, that's the complete name. But most of the time, we just use one letter. 1 farad is a big capacitance. It is a large unit. Most capacitors used in the circuit, they don't have a value of multiple farad. So most of them are in a unit and a prefix of millifarad, where milli is 1,000th, or 1,000th, 1 divided by 1,000, or 1 times 10 to the -3. That is 1 milli. Or pico. Pico is also popular. The capacitor has several picofarad. It's very common in circuit design. Also nanofarad. Nanofarad is also popular. Microfarad popular. However, let's say 1 farad, 10 farad, that's not that popular. Too large, especially for small electronic design, which means building the circuit for phone, for computer, for TV. 1 farad is just too much most of the time. Here is the example. Capacitance equals to 1 microfarad. Micro is 10 to the -6, 1 microfarad. Okay. So now we are ready to move to the second session. But before moving to session 2, any questions? Okay, cool. Second session, that's the application. Here has lots of information. So let's see. 12.2. This is one application for using capacitor, right? So far it's a circuit, and then the circuit has no capacitor yet, right? Doesn't have the 2 parallel lines. This circuit is called rectifier circuit. Anyone ever heard of like rectifier or rectifier circuit? If the answer is yes, what does it do? Anyone heard of rectifier? What is a rectifier? What does it do? So here, this circuit is one kind of rectifier, and a rectifier is a circuit that converts analog signal, such as sine wave, to digital circuit. I mean, direct current. So here has some pictures. So this is alternating current, sine wave, right? This kind of waveform is sine wave. Even though we haven't covered it yet, we're going to cover this on our last day of the lecture, which is the week before final exam week. I think that is around June. Let me see. It's about 4 weeks or 5 weeks from now. We're going to cover this. Oh, May 30th. May 30th. Is it a holiday? Huh. Around that time, around that day, we're going to cover sine wave. This is an alternating current entering to this device, and the output is a horizontal line, which is the direct current. The device, the electronic component, the equipment that's conversion is called rectifier. Now, this is the circuit of the rectifier, so it's called rectifier circuit. As you can see, input is a sine wave, and the output, the expected output, eventually is supposed to be a horizontal line. However, if you just use this circuit alone, it does not give us a horizontal line. It gives us this like bumpers, right? All the bumpers on the ground, the bumpers, or small hills. Those are like small hills. So from a sine wave, so from the center go up and it goes down and then just swing. to here, like small hills or small bumpers on the road. It goes up to 0, goes up. So this is what this circuit do, or what this circuit does. However, our expected output is this horizontal line, right? These bumpers, the small hills waveform and the horizontal line, they are different. So we can add a capacitor here. We can add a capacitor there. See, this is the new change. Look at here, this region where we're gonna add a capacitor parallel to the output RL, the load. And now this is the change to the output waveform. So it goes up and it gradually goes down, goes up, gradually goes down. So this is the waveform. It goes up, gradually go down. And if you compare that to horizontal line, oh, close, pretty close. And so adding a capacitor, we can smooth this waveform. This is one application of using capacitor. So application 1, using capacitor to smooth waveforms, to make it smooth. It's not that sharp. It's not that volatile. So it goes up, gradually goes down, and then up again, gradually goes down. Any questions? Okay. Here are this is related to this. So we know, right? Adding a capacitor make that like the waveform gradually goes down and pretty smooth. And this is one step towards the final step. The final step is to add one more device here. This device is called voltage regulator. It regulates voltage, and this is how it works. If you place this in the circuit, and if you look at here, 7805 output is, the last digit is 5 here, which means this device can provide a steady 5-volt output. Steady output, that's 5 volt. And then one pin is input. Take whatever the voltage, as long as higher than 5 volt, output will give you a steady 5 volt. And that's the final stage for this ADC, analog to digital conversion. The device here are some other applications for using this. This is called motor driver for driving motors, DC motors. The box here is just a heat sink. Okay, now here shows the second or another application of using capacitor. If you get a resistor and a capacitor connect together this way in series, a resistor capacitor connected in series, and then we measure the output voltage of capacitor, and now we made a low pass filter. This is called low pass filter. And then the picture on the right, the figure to the right, explains how it works. So first, we know it's a filter. Low pass filter means only the signal with low frequency can pass through it. So this one is a filter. Signal can go to the filter. Only the signal with low frequency can go through it. And then if the frequency is higher than certain number, it gets removed. So this is another application for capacitor. This picture shows FL means lower frequency, FH means higher frequency. Any frequency between 0 Hertz to this boundary, we keep that signal. If the signal has higher frequency, higher than FL, the lower bound, and then it get removed. So this is the second application of using capacitor. Similar to that, we have the high pass filter. This one is a high pass filter. Previous one is a low pass filter. So resistor here, capacitor there, get the output of capacitor. This is low pass. If we switch these two, put the capacitor here and put resistor there, get a voltage across resistor. This one is called a high pass filter. So it's quite similar to a high pass filter in terms of the usage. So for high pass filter, only the signal above certain range, above certain frequency can go through. If the signal is below that frequency, FH, it will be removed. So this is a high pass filter. Anyone know what kind of application we can use, or what kind of thing we can design using low pass filter, high pass filter, and actually there's one more called the band pass filter, the band pass filter. Anyone know or can imagine what kind of thing we can make, what kind of feature we can make using these filters? Okay, that's a hard question. Such as radio. A radio, let's say we have a radio, let me get a picture of it. Radio, especially the channels. Oh, there you go. That one is a old radio. It's a antique radio. I just Google and found it. So here, those are channels, right? We have AM and FM. FM frequency modulated, AM somewhere marked there. So that's the amplitude modulated. So let's say we use this, there's a knob here. By rotating, spinning the knob, we can change the frequency by changing the window. This is the window to capture the channels, such as 89.3, right? 89.3 kpcc, 89.3, right? How can we determine this is in that range? So we can make a filter, the signal, right, or the equipments only capture the signal is close to 89.3 kpcc. So to capture kpcc. So that kind of filter can be a bandpass filter. So bandpass filter is a mixture, it's a combo, it's a combination of low pass filter and the high pass filter. Making them together now is a bandpass filter. So the signal, a signal between certain frequency ranges, if it's in the range, it can go through and we can use that information. If the signal has the frequencies outside the range, will be truncated or removed, will be filtered out. And back to the radio example, let's say we spin the knob, any signal received by or picked by this antenna enter into the machine. If it's around 89.3, perhaps 89.3 minus 0.1, and 89.3 plus 0.1, and then that hertz or kilohertz, and then that kpcc signals get picked, and then the channels, right, other channel signal get removed. So this is the application of using using filters. And then as you can see, the components for making filters are capacitors. So these are, right, this is another application of using capacitor. The first one makes signal smooth. The second one makes some filters to pick up or remove some signals. The signals at different frequencies. Any questions? And another example using filters is such as microphone. Let's say here, right, the microphone I use is called Blue Yeti. I'm pretty sure most members know that brand. It doesn't matter. It doesn't need to be this brand. Any microphone can record the sound. Right? There must be some filter features because the microphone, right? Let's say we record our sound. I mean the person's talking. We know this person's talking. If there are any noise in the environment, such as airplane flying or mosquito flying and then land on the nose, or what else? Some other kind of noise. This microphone not only pick up the signal, but also remove those noise. Those noise, such as mosquito or flies are flying, that noise, the frequency of the noise are in different frequency spectrum. The person's talking, the voice is in another spectrum, frequency spectrum. If we know the frequency range of a human voice, and we only keep signals in that range and remove the noise or sound other than this range, we can get a cleaner signal. Right? Microphone can pick up a cleaner signal. So that is another application for using filters. Filters are very important in electronics, also in communication, communication specialization under electrical engineering. And here we have band stop filter, remove the signals in certain range and only keep signals in the lower band and also the higher band. Any frequency, any signal between certain frequencies get removed, cleared. And there are many other applications of filters, and there are different kinds of filters, such as here is called common filter. Common filter is very useful, is used for many use for tracking things. Let's say you build a drone or build a robot, and then the robot can track the person moving in front of the robot. So that's need to be designed using common filter. Or let's say you build a robot, maybe the Roomba, right? The Roomba robot, the Roomba vacuum robot in the house, right, for cleaning the carpet. And then there is an algorithm. There are many algorithms. One of the algorithms is related to a common filter. So wherever you travel, you kind of know if there's an internal map and also an internal path or route. And that route is generated using this feature, common filter. And then there are some other applications related to this, such as the Google OpenCV libraries. Google's OpenCV, this is for machine learning or computer vision. Let a computer with camera can see things and recognize things, such as here. Like this, perhaps it's a smart car, smart robot, autonomous car, Tesla cars, and there's a camera in front. And using OpenCV or even TensorFlow, also made by Google or maintained by Google, the camera can detect all these objects, person, cars, and then cats, dogs, you name it. And that is where the fundamental design of them is using filters. And then another feature related to filter, which is related to capacitor, is depth image. So here is a depth image. As you can see, there are a few chairs, sofa, windows, curtains, floors. Based on the color and then and algorithms, and also the hardware. Hardware is made of using capacitor, and then it can, based on the color, it can depict the how depths how deep, how far away those objects are from the camera. That is called depth image. And there are some cameras available to get. I think now, what are the Logitech, right? Logitech and some other cameras are like $200, $300, and those are the depth image cameras. The other one is called point cloud. Point cloud, I would find a picture online to see it. Such as here. So let's Google it. And then let's search point cloud. And then click on images. So this is point cloud. Also use all those stuff we just covered. They're related. So here, let's say, oh, this is a good picture, point cloud. See, here's the road, and then some trees, buildings, constructions, and then some streets. And it's mostly taken by a drone or just a car or truck. And in the drone, it has the point cloud enabled or added, installed. It scans this area and then know the 3D spatial obstacles, right? And then let's find another picture. I know there are good ones such as here, also implemented in autonomous cars such as Tesla. So by using a LiDAR stands for laser radar. So LiDAR scan this area in 3-dimensional, and then the light hit the obstacle, bounce back, and it can generate this map. And here, there's another one. I know there's another good picture. This one. That's not that good. This is good one. Or here. This is good one. This is a room and the tables, piano perhaps, and then using the point cloud feature, and I can see all the 3D dimensional with the 3D spatial. So if you build a drone, build a robot, build a rover, build a car, and it can travel, and then whenever it detects an obstacle, it can avoid it, can reroute, or can stop, or just maneuver and then stop. All these features are related to this, right? Related to filters, and the filters. And to make filters, we need to use capacitors at least. Any questions? Okay, let's see. Oh, here, this is the fourth application which is using capacitor. The circuit here has a fancy name called schematic. As this schematic is for an audio. This is speaker, an audio amplifier, and a speaker, such as let's say a person play guitar, a guitar hero play guitars, and then the guitar tone and the sound go through an amplifier, and the amplifier output the sound through a speaker. And this is the audio amplifier. As you can see here has capacitor. That one's another capacitor. This is a capacitor with polarities. Where the polarities is important, here is a variable capacitor, which means the capacitance can be adjusted by user, by the operator. So this is another application for capacitor, and making an audio amplifier. So here is another picture showing an audio amplifier. Capacitor C1, C2, they are all capacitors. Here, just another picture shows audio amplifier with capacitors. C2, C1, C3, they are capacitors with polarities. So these are the capacitors applications. And here, actually, this is one more. This is called an IC chip. IC stands for integrated circuit chip. IC chip, which stands for integrated circuit chip. There. So integrated circuit chip. And this one, if you zoom in or look closer, it shows NE555. It is a very popular chip, very popular, super popular, especially popular in around 90s, 80s, late 80s, early 90s. This chip was so popular. It's mainly used to produce a kind of signal called the clock signal. Let me get a picture of it. Clock signal. It's just square wave. A clock signal, just square wave. So this is a clock signal. So that device, wired this way, produce that signal. This signal is the like blood for smart device or for digital electronics. So as you can see, the chip here, pin 1 connect to ground. Pin 2, oh, that's why here, the clock signal. Pin 2 connect to a capacitor. See, that's the application of a capacitor. P5 connect to another capacitor. P4 connect to 5 volt. P8 connect to 5 volt. And then pin 3 is the output that generate this clock signal. And this signal enter into some other chips, also digital electronic circuits, and the circuit can work. This is the blood for those circuits. In order to make that blood, or this is the heartbeat, we need to use resistors and the capacitors. So here is the 5th application of capacitor. There are plenty of other applications. Capacitor just anywhere, everywhere, ubiquitous. So this is the end of session 2. Any questions for session 2? 12.2? Okay, how about let's move to session 3. Section 3 shows different types of capacitor. So here, this hierarchy, this tree, like a tree figure, shows the different categories and the subcategories of capacitors. So under capacitors category, and that's the biggest umbrella, it's the starting point. And then we group capacitors to 2 separate groups, 2 separate categories. One is called fixed capacitors. Its value is fixed, doesn't change. And then the other one is called variable capacitor. The value change can be changed by the user, by the operator. So these fixed and then variable capacitors. And then under the fixed capacitors, there are many, more than 3, but I only put the most popular 3 kind of capacitors. Mica, made of using some minerals, and the materials are made of using minerals. And then ceramic materials is made of using ceramic materials. And then the one we saw earlier is called electrolytic capacitor. So let's cover this first. So mica capacitor under the fixed capacitors, under capacitors. There, let's make it plural. Okay, so here, this page shows mica capacitor. Mica is just a group of minerals, natural minerals, such as silver, right? Silver is one kind of minerals in this case. Silver mica capacitors and some other kinds of mica capacitors. They are inexpensive. Last year, I bought a box about 500 mica capacitors. It's barely $10. And our classroom has plenty of mica capacitors. So 2 types of mica capacitors, clamped mica and also silver mica capacitors. And their differences are not only the materials and also these features. So first, feature tolerance. The minimum tolerance for silver mica capacitors is pretty low. It's plus and minus 1%. So which means if a manufacturer, if a company, if one person make a capacitor, it's pretty stable. The value doesn't change a lot. It changed up to 1% and then no more than, it changed either go up or down 1%. And this is a very accurate, pretty good, precise, also a much better than practical or other type of capacitor, stable. But precision, pretty precision, high precision, because its value won't swing a lot, right? It does not fluctuate. It doesn't go all the way too much or just another moment go very low. Is under this +1 and -1 range. So stable, very stable and accurate. And then the range for all these kind of mica capacitors is from 1 picofarad, pico is 10 to the -12, to 1 micro, 10 to the -6 farad. And then the working voltage rating varies from 100 volt DC to 1000 volt DC. And then the size, all kind of size. This one perhaps is like a grain of rice, right? The size is grain of rice. And here it can be like a candy, marshmallow. So the size of a marshmallow, typical marshmallow. So the size varies, depends on the space. If you have sufficient space in the circuit and then need a larger value, so you can use a bigger one. If you have not too much space, and then the value doesn't need to be super large, or use another one. Now let's move to ceramic capacitor. This one, most of them are with a disc shape. It's a circular shape, and then with 2 wires. Most of them have no polarities. Most of them with no polarities. So if you look at the legs, they have same length. Easy to tell. So a ceramic capacitor is made of using ceramic materials and as dielectric. Where the materials inserted between the plates. So that's called dielectric. And if you use that material, if you use ceramic material for that, that's ceramic capacitor. Application like laser power supply, and also power circuit breaker, DC-DC converter, which is called a buck converter or boost converters. Tolerance, the minimum tolerance for class, by the way, there are 2 classes. For ceramic capacitor, there are 2 classes. Class 1 is still pretty good. Class 2 is not that good in terms of quality. So class 1 more expensive, quality is good. The tolerance is still can be as low as +1 -1%, plus and -1%, which means high precision, very stable. The range, working range is same. The value range is also similar. However, class 2, as you can see, the value varies a lot, right? It can go up or go down 20%. It's like let's say the price of the stock. Let's say we couldn't buy a stock, and then at this moment it's $10. After 2 minutes, and it is 15. And then after another 5 minutes, it's $2, right? It fluctuates too much. That's not good. Well, we prefer it to be stable, predictable. But here is plus and minus 20%. It's not stable. That's why it's low precision for class 2 ceramic capacitor. Not stable, typically plus minus 15% for this kind. That's the range of the value. This is the range of voltage The size for both classes or size. Most of them are small as a grain of rice. And then the big one can be like a the coins, the pennies, the size of a coin. Now we move to the third kind. This is more useful for, they are all useful, but these are more common for circuit design, but not this. So here, those are electrolytic capacitors. Most of them, they have cylindrical shape. So if you zoom in, here, this is cylinder, and the two legs. The leg connect to the strip with the minus sign. This is not a bubble. It's not a circle, not an oval, it's a minus sign. That means this leg connects to the lower voltage in the circuit. The other leg connects to higher voltage of the circuit. And sometimes we can easily see based on the length of the legs. However, when we build a circuit, we also cut those wires, right? We truncate them. We cut the wires. So if the wires are cut, we may not able to tell the positive or negative, the polarity just based on the length of the legs. So we use the strip here. This is the 100% guarantee. And then for this kind of capacitor, polarized, which means it has polarity. The orientation for putting them in the circuit is crucial. Precision, high precision. However, there's a big problem. This can leak out there. Low breakdown voltage, and it can leak high amounts of leakage. Leakage means when this is charged, it can be discharged. It discharged by itself if you put it there for a while. Let's say we have a cup of water. Right? If we have a cup of water, if it doesn't leak, the water, let's say 1 gallon or 16 ounce, right? If you put the water there for a day, so it's still 16 ounce, unless it's vaporized. But for a cup that leak water, water leaks through some holes on the cup. At the beginning, it's 16 ounce. Maybe after 2 minutes, now it becomes 8 ounce. So that's means leakage. Similar to here, if this is fully charged, and after a while, it's not fully charged, it's halfly charged. That means it has high leakage. That's the bad thing about it. We want to have a container that can hold a charge firmly. This is the drawback. However, it's pretty high precision. And then the range, the value of it is from 1 microfarad to 200,000 microfarad or 200 millifarad. This is the voltage rating, and here is the dielectric constant. Very soon we're going to cover the dielectric constant. Any questions? Okay, cool.
No questions, sir.
Oh, thank you, Edward. So this is the most popular one in terms of building circuit. Ceramic and nickel capacitors are also used, but these are the most popular one, most available. Okay, let's see. Oh, here, this is another kind of just different model, different design. In term of features and performance, same, just different way to build a capacitor. Instead of putting both legs on one side, now one side has one leg, like a sausage here, a chorizo. So one wire, the other side. That's also a pretty common, but those are more common than this. This perhaps for wiring this, for certain wiring, we have to pick that. And then for this, we just place this on top of the PCB board. But in terms of features, they are same. So here again, the side with the strip with the minus sign, its leg connects to lower voltage. So the other side normally has a longer leg connect to higher voltage in the circuit. Otherwise, right, if you flip it, there's a chance this can be exploded. There's a chance. If it doesn't explode, it just doesn't work properly. Oh, here, that's a good picture. So here shows the saturation capacitors are all exploded or broken. These four with the material residuals on the top on the cap. That's even worse. It's like they will meet. The things come out from the stomach and then left from the head, left from the mouth. No good. And those are bad also. This capacitor, they have a round head. If the side, the head is not flat, in this case, round, that's mean bad, it's broken. They cannot be used anymore. So we have to take our soldering gun, desolder it, and then unplug these broken capacitors, and then buy equivalent capacitor, put it back here. So step one, take our soldering gun, heat this up, and then flip the board, desolder the other side, desolder capacitor, unplug them, and then look at the numbers here, such as here it shows 2,200 microfarad works under 6.3 volt. And then there are some other stuff, 6.3 volt. And then enter this number in the eBay, in Mouser.com, in Amazon, wherever, Alibaba, Taobao, whatever. And then find the equivalent one. Once you get it, insert the newly received capacitor back to the board and then solder them, trim the extra wires. They should work, or at least this part of the circuit work. If this is residual, let's say capacitor exploded, and this material, this chemical residual, and then split to other part of the circuit, there is a chance, the chance is not that high, but there is a chance other part of circuit can be damaged. And also, a capacitor is in my opinion, is the number one fragile thing. So if the circuit is not working suddenly, such as it works 2 hours ago, now we try to use the monitor light blinks, however, screen doesn't turn on. It's just a black screen with a blinking light there. And we try many features, try to troubleshoot, doesn't work. There's a higher chance the capacitor inside is burned, is exploded, or is broken. So you may need to replace the capacitor, and then hopefully that monitor go back to work. And then this is another device, also pretty fragile, same as or similar to capacitor in terms of how fragile it is. It's called this is IC chips. Most IC chips are fragile. They are sensitive to heat. We cannot put this on the board directly. We cannot solder this on the board directly because the soldering gun reach to let's say 300, 400, 500 degrees, and the tip of the soldering gun touch here. The high temperature can burn the materials inside. Those are silicon materials inside the chip. Can burn that easily. So to prevent all these things from happening, we put this on the board first. This is called socket, the chip socket, the IC chip socket. So solder this on the board, and once this is fully soldered, completely soldered, and then insert the chips on top of the socket, and then it work. Another good thing for using socket, let's say for any reason this chip is broken, we can simply unplug it from the socket. We don't need to solder, desolder. We just unplug it using fingernails, right, or using tweezers, using screwdrivers, and then put another one here. That's the reason for using this socket on the board, PCB board, where PCB stands for printed circuit board. Any questions on this page? Okay, cool. Here, before using capacitor, or even before measuring its value, we need to discharge capacitor as a good practice. So not all, but many, especially nowadays, many multimeter, such as that one, has a feature to measure capacitance, such as here, this one. Oh, if you spin the knob here, if you spin the knob, spin to here, not the omega is the other one. So spin the knob points to here, and then click on the yellow button. So this multimeter start or can measure capacitance, how large the capacitor is. Or using a more professional device, this one. This one is called LCR meter, handheld LCR meter. Where L, we haven't covered L yet. And next Monday, we're going to cover L. L is inductor. C is capacitor. And the R is resistor. So this is a meter measure L inductor, inductance, right? The capability of inductor, which is a coil, and then capacitors, and also resistance. This is for LCR meter. Before measuring it, we need to discharge the capacitor. In case we, let's say for some reason, for any reason, or some other technician or engineer use this capacitor and there are some charge left inside. Even though those legs, the capacitor was disconnected from the circuit, and it's still possible to, there are some charges left inside. So to discharge it, we can just connect the legs together or use a screwdriver. And then this conductor touch both legs. And now capacitor is discharged. And this is a very useful technique. Let's say capacitor, right? Capacitor in the microwave store lots of charges. If you replace it without discharging it first, there's a chance we can be electrocuted. Even though we shut down the circuit breaker, turn off the power, and then the capacitors inside still holding lots of charges, high current. So the first thing to do before uninstalling, before disassemble, before removing it, use a screwdriver or make sure discharge it. So in other words, let's say this capacitor, even not this one, is a fancy one using microwave. And then we shut down the circuit, we open circuit breaker, shut down the electricity, turn off the electricity. There's a chance the capacitor still hold the charges. So we need to discharge it. That's a good practice. Again, to discharge it is easy. Just connect the two legs, perhaps using a screwdriver. This screwdriver, I mean, this side of the handle is plastic, so insulator, you won't touch the electricity. And here the metal piece connect these two legs and discharge capacitors. Now we've finished 12.3. Any question on 12.3? Any questions before we move to 12.4? Okay, cool. So 12.4, the factors that affect capacitance. And in this chapter, in this session, we have a very useful formula. So let's see. We have the capacitor. This is a capacitor with two plates. And then those two plates are conducting plates. A capacitor is like a swimming pool. For swimming pool, a big container store water, right? Water molecules or water. Over here, this capacitor store electrons. Same thing. And here we get a mug. A mug is also another small container, store little water. Swimming pool is a big container, stores lots of water. Okay, so here, again, the two vertical lines, this is the schematic symbol for capacitor. And this vertical line with a curve is also a common symbol for capacitor. The difference between this and that is this one specify that particular capacitor in use has polarity, or polarity is crucial, it's important. If you see a circuit with that one, means polarity is not important, or it doesn't have polarity. If you flip it, it doesn't matter. The circuit doesn't, no effect, doesn't damage, does not get damaged. So now, but let's see, we have a capacitor and then we put some materials inside. This green material is called dielectric material, or in short, just called dielectric. Now, okay, let's do an analysis. Let's analyze capacitors and to see what are the factors that affect capacitance, which means the capability of capacitor. So here, let's say we have this capacitor, and we assume the area of the plates, the two areas, they don't change, remains constant, remain untouched. We are not going to replace the plates. The size, the dimension of the plates for both plates remains same for the first experiment. The only thing that's changing is the distance separated by the plates, the separation distance. So this is the first trial. And now, well, let's put the plates apart, put the plates further. D2, the second distance. And now, how about let's try the third one. The third distance, and then the distance between the plates are even further. And now let me ask a question. Among these three, right, this, that, here, which case, which scenario capacitor, it has the biggest capacitance? Which one has the biggest one, or do they have same capacitance? So let's say this is the first one, the first trial, the first scenario. The plates are close to each other. This one not that close. Here very far. The question is, among these three different scenarios, which one has the biggest capacitance? Or they have same capacitance? Anyone? Okay. If this is not easy to find out, how about let's use analogy? Let's use analogy. And let me use extreme case. Let's say here, and let's look at our first case. Let's say this plate, right? We install a giant capacitor plate. We are building a giant capacitor. This plate is in downtown LA. This plate, right? We put it there next to maybe the Staples Center. Oh, now it has different name. Let's say this is in the right in the center of downtown LA. And then now we're gonna move this plate maybe adjacent to it. And later we move this with the second plate to a little bit further, maybe to Palmdale. Let me see. or Mojave, right, to Palmdale or Lancaster. And now we still want to move this away or apart. Let's say now we continue moving the second plate, this plate further to New York City. Right, the first plate is still at downtown LA, and then the second plate eventually moved to New York City, the downtown of New York City. So if you look at here, I think we already know which one has bigger capacitance. The third case, right, the plates are too far. If we put electrons on one plate, those electrons, because they are too far away, the influence of those electrons and the electrons on the first plate are too weak. And the influence are too weak because the electrons are too far away. And some electrons on the first plate are in downtown LA, and then the electrons on the other plates are in New York City. The attractions between the electrons on both plates are very weak. So now we can predict, right? Based on this analysis, we can predict the capacitance, which means the measure of the ability of capacitor is inverse proportional to distance. The further away, bigger distance has small capacitance. If you place the plate, if you put the plates very close to each other, and they have relative bigger capacitance. So let's write this down. So here, if the plates are close to each other, bigger capacitance. If the plates are far apart, a small capacitance. So this is our first experiment. Any questions here? Any confusions here? Okay, cool. Now let's move to the second analysis. And now, this is still the first one. How about now? We keep the distance constant. We are not changing the distance between the plates. However, we are changing the area. The area of the plates. So for the one to the left, small area, right, or the original area. And then later we are changing the area of the plates. We make them larger. The question is, which one has, right, either the circuit to the left, capacitor to the left, or the capacitor on the right hand side, which one has bigger capacitance? In other words, which one can store more electrons?
A larger area.
Yeah, that's right. Exactly. Yeah, very good, very good. Excellent. So this one, the larger, the one with larger plates can store more electrons. So this one has bigger capacitance. So from previous trial, previous experiment, we know distance is inverse proportional to capacitance. Further apart, weaker capacitance. Close together, bigger capacitance. The second trial, second experiment. From here, we know that's the conclusion. Bigger area of the plate, assume both plates have same areas. Bigger area, bigger capacitance. Small area, small capacitance. So area is proportional, right? Direct proportional to capacitance. Or capacitance is direct proportional to the area. Now, how about this is a special case. If you move the plates, in other words, the plates are not 100% overlapped, it's partially overlapped. We only can count the regions that they are overlapped. And this is not good. To maximize it, we need to make sure all the plates, right, the plates are 100% overlapped. Otherwise, we are wasting material, wasting space. Wasting space, right, take additional space, but degrade downgrade or degrade the quality, the capacitance, the ability of it. So that's our second trial. The third trial, not here yet. Let me see. Yes, the third one is this. Let's say here we have a capacitor, and here we get this, assume everything remains the same. The only difference is we put some materials inside. So here I give the answer. The one to the right has better capacitance. That's the reason we put the material. We want to improve the capacitance. And then we put the dielectric materials inside just to improve it. Actually, this is the best way to improve capacitance. So now we have three things. We're gonna put them together and then make a formula. That formula is this. However, we're gonna cover this formula just in a few minutes. We skip some slides. So the third thing is called dielectric material and then dielectric constant. This table gives us an idea about the material can be used to improve capacitance. And then how many times is better than using air or putting nothing, using vacuum. So if it's air and a vacuum, let's say is 1, right? Reference number 1. If you use the Bakelite, the capacitance is improved almost 5 times, right? 4.9 times. If you use fused quartz, the capacitance is improved 3.78 times. And then neoprene rubber, 6.7 times, nylon, 3.4 times. If you just put regular paper, it's improved 3.7 times. And so on. Silicone oil, Teflon, water, strontium titanate, they are all dielectric. And this table and the number should be given when we solve problems. There is a question on test. No. There's a question in the final has a question about this. We're using this. So the table is given. And now let's see what is that dielectric constant. It's called, it has a fancy term called relative permittivity. So permittivity is just a term to describe how well a material can be used to improve the capacitance. And then relative permittivity is how well the material is better than the reference material, which is vacuum. A vacuum is not a material, but that's just an environment. In vacuum, using double plate capacitor can store charges. It's the poorest condition. Adding materials between the plates improve it. So here, such as adding Bakelite, comparing to vacuum, capacitance increased 4.9 times. It's 4.9 times better than putting nothing in the plates or putting vacuum in the plates, putting air inside it. That is why it's called relative, related to relative to vacuum or air, comparing to vacuum and air. Those are the reference material, relative permittivity. And then here, this is the symbol. This symbol does not call E. It's a Greek letter and it's called epsilon. Epsilon. That's the name of that symbol. Epsilon R stands for relative permittivity. Permittivity. So this is here. Relative dielectric constant or relative permittivity. How well this material is better, right, is comparing to vacuum in terms of storing charges. So now we look at its formula. Not this one here. Capacitance, it is proportional to the area, right? Based on our earlier analysis, bigger area, better capacitance. So it's proportional to it, and also inverse proportional to distance. Further apart of the plates, downgraded, right, degrade this capacitance. And then if you place the plates closer to each other, right, the distance decreases, capacitance increases. And then they're also proportional to this material. So together, this 1, 2, 3, three quantities together, it can be used to figure out the capacitance. This is the very important formula. We have one final exam questions. I use this under the table to figure out a double plate capacitor's capacitance. How about now? Let's solve a problem. Let's solve an example. So here we have a double plate capacitor there. Both plates, each one, both of them are square plates, square-shaped plates. The plates, they have same sides, and each side of the plate, for both plates, 2 centimeters. If both plates are separated by 1 centimeter, right, from here, this plate to that plate, the distance is 1 centimeter, and then the material, the yellow material in between the plates is silicone. And then we want to find the capacitance of this capacitor. So let's use our formula and find out. Please put this formula, on cheat sheet. This one. Please put this on cheat sheet. Let's spend 40 seconds and put this on cheat sheet, and then we resume after 40 seconds. This formula is so useful, and we need it at least 2 more times. One for homework, one for final exam. So let's take some time, make sure put this, we're already done, and I put that on cheat sheet. We resume very soon. Okay, so let's continue the example. We need that formula. So first we need to find the area of a plate. So area, this is a square shaped plate. So the area is the side times side, which is the side square. So here, each side is 2 centimeters. How about let's convert centimeter to meter? This is a rule of thumb. I suggest anyone working on this kind of question, convert whatever the unit to SI unit. The reason is, if you look at a table here, or just a number we're going to use later, this number, oh, I skipped that one, is farad per meter. So it's based on meter, so we need to use that. So let's find the area first, and then go back and cover the missing thing. So 2 centimeters equal how many meters? We know 1 meter is 100 centimeters, but this is defined. 1 meter is 100 centimeters, but we want to know 1 meter equal to how many meters? 1 centimeter equal to how many meters? Right? We know one way, from meter to centimeter, but we want to know the opposite way, from centimeter to meter. So we can do following. We can divide 100 on both sides. So let me add one more step. So 1/100 meter equal to 100/100 meter. Right, so from step 1, we divide 100 on both sides of the equation. So 100 divided by 100 cancel out. And so only 1 meter left. So this is 1/100 meter equals to 1 meter. I know there are lots of steps. There. Okay, so now how about let's swap it. Right, we flip the equation. Oh, sorry, this is centimeter, missing the centimeter. So we flip here. We put 1 centimeter to the left, and then we put this to the right. And now we can figure out the conversion. 1 centimeter is 1 divided by 100, 1/100th, which is 0.01 meter. So now we're going to use that. So let's copy this. No. So this one, 2 centimeter square can be replaced by 0.01 meter. From previous step, we replace centimeter. 1 centimeter is 0.01 meter. We replace that by this. So 2 centimeter is equivalent to 2 times 0.01 meter. And now we enter this number into the calculator. We get following number. So from here, 2 times that equal to 0.02, and then we square it. Once we square it, it's 0.0004 meter squared. So this is the area of each plate. Are there any questions here? This is a part that might not be too easy because there are lots of maths here. What question? Okay. So I think there are no questions. We can continue. And the next thing, we need to know the distance between the plates. But this time is 1 centimeter. And if you move the decimal point to the left twice, that's meter. Move it to the left twice, 1, 2 is 0.01 meter. So now we did a conversion. We can do the same thing for previous one, right? Move the 2 decimal to the left twice. So we get 0.02 meter. So they all work. Before continue working on here, let me cover the part that I missed. So here. So this is the formula where epsilon is the permittivity, which means how well this can store charges for that material alone, such as for nylon, for Titanic, for Teflon, for paper, for wax, for oil, whichever the material. And then is epsilon 0 is the permittivity for vacuum. That is a constant number, 8.85 times 10 to the negative 12 farad per meter. This is how well a vacuum can be used to store charges. Right? This is the actual number. And then this is a relative number, epsilon R relative, such as water is 4 times better than vacuum. So this is 4. Teflon is 7 times better, so that's 7. This times the one for vacuum is the real permittivity, called the absolute permittivity of the material. So we're gonna use this formula. Please put this on cheat sheet as well. This one and this number, they are very important. Please put this on the cheat sheet. Everyone need to use this at least 2 more times. Homework once, and then final exam the second time. I think question number 3 in the final, question 2 or 3 is about finding the capacitance of a double plate capacitor. The question is just very similar to this problem, very similar. You can also take a note here. When you work on the final, may refer this video or chapter 12, slide 125 or 120, 30-ish, 134, yeah, 133. Okay, now we know the area now, and we also know the distance between the plates. It's time to find the capacitance of this double plate capacitor, a parallel plate capacitor. C equal to epsilon, this is the absolute permittivity, times the area and then divided by the distance. So epsilon, here we are using a given silicon. Silicon on the table should be given and is given. Silicon oil is 2.5, so we put 2.5 here. And multiply the absolute permittivity for vacuum. 8.85 times 10 to the negative 12. The unit is farad per meter. And then multiply the area, right? Area we calculated 0.0004 meter square over, right, divided by the distance 0.01. So here is the most important formula over here. 2.5, let me use different color here. 2.5 is there. This one. Because we are using silicon, and because it's mentioned, right? The material, the dielectric material is silicon, not vacuum, not bakelite, not nylon, it's silicon oil. And that has a relative permittivity 2.5 times the permittivity of air of vacuum 8.85 times 10 to the negative 12. Together is called the absolute permittivity for silicon oil. Multiply the area here, we calculated, divided by the separation distance D, and now the rest of the work just to enter these numbers into calculator. So I entered this into the calculator. This is the number we got. 8.85 times 10 to the negative 13 farad, very small capacitance. Small capacitance doesn't mean it's useless. It's very useful. You use for something else. Used for many things. Any questions on this example? The thing we need to be careful is make sure here always convert a unit to an SI unit. That will guarantee the answer is in the right direction. If you forgot to change it, and no matter how many steps we do, the answer is not right. So make sure always change here from centimeter to meter. The reason is the number shown here, and also that permittivity of vacuum is in terms of meter per second. So we need to change all these centimeter, inches, or feet, if there are any, to meters first. For our final exam question, not that complicated. So no feet, no inches, just change from centimeter to meter. Okay, let's see. Now we move to the last session, 12.5. 12.5 is called the series and the parallel capacitors, which means different ways to connect capacitors. There are simply two ways, series way and a parallel way. We know the connection. However, for capacitor, there's a big difference. So let's see. So if we have n capacitors, right? Capacitor 1, C1, C2, C3, and all the way to the last one, Cn, n capacitors connected in series. This is not, we cannot add them up. Capacitor is different, special. The total capacitance is not adding them up. Actually, we have to use the other formula. That is here, the reciprocal formula. This formula, right, to everyone, this is not new. We have seen this before when we learn resistors. Connect resistors in parallel, and now we have this reciprocal formula. 1 over the total capacitance is the sum of the reciprocal for every capacitor, and then we find the sum of them, sum of the terms. There is a way to prove it, but the proof is not that easy. Also, that requires more information, more knowledge. So how about let's skip the proof. That one is hard to, kind of hard to understand. So let's don't worry about the proof. Let's just know this is the formula, formula to find the total capacitance if we have capacitance connected in series. This is opposite to finding the resistors connected in series. When we have resistors connected in series, we add them up directly. And then the sum of all the resistance is the total resistance. For capacitor is different. So let's have some examples. Here, we want to find the total capacitance CT for following circuit. C1 is 100 microfarad, C2, 120 microfarad, C3, 240 microfarad, and a C4, 680 microfarad. We want to find the total capacitance. In other words, if we remove, or if we throw this away and replace this 4 by 1 capacitor, what's the value of it? So we're going to use that formula to figure this out. At least it's the number in theory, conceptually. 1. But we write down the formula first. And we write down the formula, and since there are only 4 capacitors, we only need 4 terms. Only 4 terms over here. And now let's plug in numbers. This is just one way to do it. Let me see, do I have a better way? Let's go back here. I try to just cover one formula. Let's cover these two. These two formulas are the same. Right? The second formula, just one more step for using the first one. If we take reciprocal on the left, 1 over CT, that's CT. The right-hand side, we also take reciprocal. So it's 1 over the whole thing together. Is 1 divided by all of them. So 1 divided by all of them. So now this is another version of the formula, right? In other words, we just reciprocal on both sides. Reciprocal of this is CT. Reciprocal of the right-hand side is 1 divided by the whole thing. So this formula is same as the other one. Okay, now let's use that formula here. We know that one, right? We can find the CT, just reciprocal it, and then we just take 1 divided by whole thing. So 1 over C1, C1 is 100 microfarad. C2 is 120 microfarad. C3 is 240 microfarad, and C4 is 680 microfarad. Right, so now the rest of the work just to enter these numbers into a calculator. I will show how to enter it. There are some steps we need to be careful. But before me showing how to enter this in the calculator, are there any questions? Perhaps can also write this down. So at the time I show how to enter this in the calculator, you can compare the equation with the expression in the calculator. Okay, so I'm going to bring the Google Calculator page here. So here, this is the Google Calculator. I just enter Google Calculator and then there. So first we use 1 divided by open parentheses. This is very important. Make sure it's 1 over parentheses. It's a common mistake. When I have the DC class, the next level class, I remember a few students had the issue most of the times, forgot to enter the parentheses, and then the answer at the end is wrong. Many times they made the same mistake. So 1 divided by, and the next thing is 1 over 100 plus 1 divided by 120 plus 1 divided by 240 plus 1 divided by 680. So here is the expression we had on the PowerPoint. So 1 divided by the whole thing, and for the whole thing is the 4 reciprocal terms: 1 over 100 plus 1 divided by 120 plus 1 divided by 240 and then plus 1 over 680. Hit equal. So 41.72. 41.72. So if we go back to here, and then compare this, it shows the 41.72. Right? That's the expression. This is the answer. So now we know, wow, the total capacitance of the system, the value is smaller than any capacitor's value. So this is a way to really downgrade, right? Downgrade the capacitance. Using more capacitor and not improving, actually deprove it, make the total capacitance smaller. So in other words, maybe we should not connect them in series in general. The total capacitance actually decreased. Any questions? So far, so good.
Professor, would you be able to repeat the step in the, is it you're dividing, it's 1 and then divided by 1 divided by the 100 microfarads plus, and then 1 divided by, okay. Thank you.
Yeah. You're welcome. Here, every term has microfarad. So I just omit the unit over here, just enter the number since every term has microfarad. And then just get a number. And I know at the end, since every term is microfarad, the result must be microfarad. For our class, where we have easy numbers such as here, most of the time we don't need to worry about different prefixes, such as this is micro, maybe the next one is milli, and here we have pico. No, we don't. For our class, the intro class, we don't need to worry about that. In case, right, for any situation, we have a problem that they have different kind of prefix. we can align them, such as we can convert a number with no prefix and for all of them, and then just combine them, get an answer, right? Let's say this is micro, the other one is milli. So how about let's get rid of micro, convert this to a number with no micro anymore, convert this with no milli anymore, and then now we can combine all the terms. But back to here is 1 divided by the entire thing, which is 1/100, 1/20. Let me take a screenshot of the calculator. The calculator expression we entered earlier. There we go. So here. So this is that the calculator page. So it's a 1. This one is that one. Is this one on the top, that one. Divided by parentheses, but this parentheses is everything in the denominator. The first term in the denominator is 1/100. Second term is 1 divided by 120, 1/20. And then the next one is 1/240. And then the last one is 1 divided by 680. And how about next? Let's see. Oh, this shows another way. So here shows another way to solve the problem, which is same, actually same. So here we just use the general, the most common formula, the reciprocal formula. Right, this is 1/100 microfarad, 1/120 microfarad, 1/C3 is 1/240 microfarad, and then 1/, this is 1/680 microfarad. Now we take our calculator and add them up. After adding them, I get this number. Don't worry about the unit because they all have microfarad. The answer at the end must be some number followed by microfarad. So don't worry about this, otherwise we'll be very confused. So after enter these numbers into the calculator, I got this. However, this is 1/CT. It's 1/CT. We want to find the CT, so we take reciprocal on both sides of the equation. So 1/CT is CT, and this is 1 divided by the number, which is here, 41.72 microfarad. So both ways we get the same answer. Any questions? Okay, so let's see. Here we get another example. It's a special case. And this is a special case. We only have 2 capacitors connected in series, right? So let's step back. From here, we know many capacitors connected in series will use the reciprocal formula. And if you have 2, there is a shortcut formula, like resistors. That's the shortcut formula. That's the one. Please put this on cheat sheet. But this formula is not new. But when we covered 2 capacitors connected in parallel, the parallel circuit for capacitors, we have seen this formula. Now, if we have 2 capacitors in series, we use the same pattern. And so please put this on cheat sheet first, and then very soon we're gonna work on that example. So okay, let's see. There, 2 capacitors connected in series, 100 microfarad and 120 microfarad. And then we want to find the total capacitance. Now we can use the shortcut formula. This is not a shortcut formula. This is just a reciprocal formula with two capacitors. Using the shortcut formula, that's the one. The total capacitance is first capacitor's number times the second one, such as here, divided by first capacitor's value added to the second one. This is very similar, right? Actually, same as the parallel capacitor formula. Right? C1 times C2 over C1 plus C2. Now, how about let's plug in numbers? C1 is 100 microfarad. C2 is 120 microfarad. And here, for the denominator is C1 plus C2, so that is 100 microfarad plus 120 microfarad. Any questions over here? Now, this is not new, right? That's not new. We had this formula. I think the first time we seen it is in chapter 3 or chapter 4, but that's used for resistor. Two resistors connected in parallel, and then we have this shortcut formula. Okay. Now the rest of the work just to enter this numbers into the calculator. So 100 times 120 divided by 100 plus 120. And then using calculator, I get 54.55. And then the unit is, they have same microfarad. So answer is microfarad, the total capacitance. So this is how we find two capacitors connected in series. Let me have a summary here. If capacitor connected in series, the total capacitance of the system is degraded, downgraded, not good. It does not increase, but it decreases. Not too much usage. But now we move to another way to connect them, put them in parallel. If we put capacitors in parallel, we actually improve the total capacitance. And I think as most members have guessed the answer, have guessed the formula, the total capacitance just simply add them up. The total capacitance is the sum of individual capacitance. In other words, the total capacitance is C1 plus C2 and plus perhaps more capacitors, C3 plus all the way to Cn. So this is how we find the total capacitance. Easy, but this is easy if you place capacitors in parallel. So now that's just the same information as below there. Let's solve this example. For this one, example 8, we have two capacitors, C1, C2. We want to find the total capacitance of the circuit. And then we know they connected in parallel, so easy, right? Easy for parallel circuit for capacitor. We can simply add them up. CT, the total capacitance, is the sum of C1 and the C2. So C1 plus C2. And the plug-in numbers is 220 pico plus 470 picofarad. And then the result is 690 picofarad. So as you can see, this is pretty easy, right? When we connect capacitors in parallel, that's so easy. We are improving the capacitance system. The total capacitance is improved, increased, expanded, right? Rather than with putting them in series is decreased, deproved, shrinked the value. let's see, we have another example here. What's the total capacitance of that circuit? Here we have 5 capacitors, specifically C1, C2, C3, C4, and C5. And we want to find out the total capacitance. The total capacitance is just the sum of all these capacitors. So we simply add them up here. So a plug-in number, C1 is 100 microfarad. C2 is 200 microfarad. C3 is, here, 100 microfarad. C4 is 200 microfarad. And then C5, this capacitor has 470 microfarad. Add all these numbers, and then we get 1070 microfarad. If we leave the answer, this is right, but we can improve it. Right? We can move the decimal point to the left 3 times, and then improve this number 1,000 times. So this is 1.07 microfarad. Right? Move the decimal point to the left, which means divide the number 1,000 times to here. We have to multiply 1,000 to the prefix. Micro is -6. Multiply 1,000, that's -3 milli. So the answer, either the first one or the second one, they are all good answers. The last one is better. It's 1.07 millifarad. So this is the end of this session, or the end of this chapter. Any questions? So this is the capacitor chapter. Let's see. We finished 2/3 of the chapters. So let's see. Give me 1 minute. Let me log into Canvas. So here, this is our Canvas page, the home page, right? Canvas homepage for our class. And what is this? Course evaluation. I think that's a new activity about the company we are working with. I see. Okay. Oh yeah, it is. Yeah, we're gonna have one more assignment. So we're gonna have one more homework. So far we have 5, right? We have 5, 1, 2, 3, 4, 5, and there's one more. This one is fun. It's fun, and it's about using a virtual reality application to see transformers. To see how a transformer look like. But I'm still working on it. Give me maybe 7 more days, and then that should be available. Shouldn't take lots of effort. Okay, let's see. Let's go to the home page. So far we covered chapter 1, atomic structure, the basic concept of electricity, Ohm's law, and then electricity, scientific notation, and the metric prefixes, series and the parallel circuits. This is the session we have the parallel circuit. And then we've seen that formula for parallel resistors. Chapter 6, voltage divider circuits, Kirchhoff laws, and then series parallel combination circuits. Today we cover chapter 12, capacitors. And then next week, we're gonna cover inductors. And after this, we just have one more chapter, This is chapter 1 of the AC book. Is called the alternating current. We do have one more test. So today we finished chapter 12. Today is April 18th. And 1 week from now, that's April 25th. Here, next Monday, we will finish chapter 15. How about this? We do have class next week. And then after finish chapter 15, I make test 2 available. So that should be available. And the week after 25th, that's May 2nd. So May 2nd, let's have test 2 due on the day. And let's have test 2 due on May 2nd. So let's see here. So let me create a test 2. Not this one. Okay, this one too. So let me change the date, and then I'm gonna edit the content. So click on here. We're gonna have test 2. Now, quiz there. And then, so we're gonna have test 2 here on this day. Oh man, test 2, and right, today is 18. We finished capacitor chapter 12. And then next week, we cover chapter 13, inductor. And then the following week, let's have test 2 completed. So it's due midnight of May 2nd. I make it available on 25th. And that's available until May 2nd. There. And the test 2 only cover, test 2 only covers, let's see. For for test 1, right, it covers chapter 1, 2, 3, and 4. And then for test 2, it covers chapter 5, 6, and 7. And so only 5, 6, 7. Actually, only 6 and 7. Right? Only 6 and 7. Test 1 cover chapter 5 also. So only 6 and 7 for test 2. So let me put a note here. So we should start preparing. Of course, it's still take home. So let's see. Test 2 there. So it covers chapter 6 and 7. And it's open book, take home test. And this test will be available next week after class. And everyone can spend the week to complete it. The due day is the following week, not next week. Next week is the time we can begin working on it. And then everyone can spend a week to work on it. It's not a lot. It's designed for a 3-hour exam. And then the last day to work on it is May 2nd. So that's for test 2. And then we follow the same format as test 1. And that day, May 2nd, we are not going to move forward. Instead, we use the time to work on test 2. I'll be on Zoom. If anyone need hints or want to use the time to work on the test 2, feel free to use the time. But that test is available next Monday. So this is our second test. And then after that, we have a final. Final exam should be the first week of June. If I remember the date, the first week of June. Let's see. LATTC. And then click on not services. Yeah, all services, here. Homepage. And then let's see, this is the spring schedule, spring, click on it. And then the important or final exam date, final schedules. If you look at here, our class is Monday evening. And Monday, so this is Monday class. So Monday, if the class starts between 6 and 8 p.m. Monday only, that belongs to our class. So our exam is from 7:30 to 9:30. However, final exam format structure is same as test 1, test 2. I will make it available at least a week before the due date. The due date is 7:30. It's the midnight of June. Oh no, it's May 31st. May 31st. Is it? Let me see. Oh, that's Tuesday. June 6th. Yes, can be June 6th. Then I'll make it available on 30th, so everyone can work on it on 30th. And the format is same as test, so is take home also open book, and that specify, right, that mainly cover the last 3 chapters. Even though it's cumulative, one question is about chapter 7. One question is about chapter 7. That's a very important chapter, series parallel combination circuits. One question is about chapter 6, divider circuits. And then the remaining 3 questions are from chapter 12, one question, chapter 15, and also the AC chapter. That's for final exam. But we can talk more about it after test 2. We have 1 month, over a month from now. But this is the remaining, the plan for the remaining things, exams and final exams. Any questions? So next Monday, we cover chapter 13. That's the inductor chapter. Oh, sorry, chapter 15. Chapter 15 is the inductor chapter. If you have some spare time during the week, please start reading. Please read chapter 12. That's also the reading assignment. And also start reading chapter 15. It's an interesting, useful, and not very easy chapter. Inductor is quite complex. So may start reading them. Oh, why this is not actually unchecked. And then we have test 2. And let me look at the assignments. Again, one extra assignment will be available. This one should be fun. It's using a 3D application to see a transformer in 3-dimensional. And then, so for now, we should work on this one. Voltage divider should be completed. Today, we can work on, no, I take this back. We still need to cover inductors, so we can work on this. So let me put this due date. This due date should be April. Today is April 18. Next week we cover 25th. So the suggested due date is May 2nd. However, for all assignments, everyone can turn in all the assignments by the end of the last day of the semester. So assignments here are helping everyone for preparing the exams. So you can try many times. The system just picked the highest grade at the end. And so here, time limit, no time limit. Multiple times, yes. Multiple attempts, yes. And then system will pick the high score, a score to keep. Attempts unlimited until the last day of the semester, which is the final exam day. Okay, so let me put this test. This is the new test. Put this here. It's not available yet. I'll make it available next Monday. Remove this one. Any questions?
Professor, is there any homework covering chapter 6?
Chapter 6, let me see. Chapter 6 is divider circuit Kirchhoff. Oh, yes. So the homework related to chapter 6 is this one, assignment 4. So if I click on preview, here are the questions. This is the voltage divider circuit. So given R1, R2 voltage from the provider source, we want to know what's the voltage across R2. And then this is the second one. Yeah, there are only 3 questions. But the last one has many options. So make sure get a calculate and then get a correct answer and select the one that close to here. This is a question. I think a question. Yeah, we did cover in class. But this is a question require using the cross multiplication, which is not very easy. This question is not super easy, but there are examples. So assignment number 4.
Okay, I've already completed that one.
Oh, that's great.
So I was looking for more of the Kirchhoff's.
Oh, Kirchhoff law.
Yeah.
I can add, maybe I can add another assignment and that will have some Kirchhoff laws problems. Kirchhoff law, no, in the class I told everyone, no, we won't, because Kirchhoff law can be so complicated. For our class, we just know the present of KCL, KVL, but Kirchhoff law, let's see. Kirchhoff law problems. Without solving these problems, let's see here. Let's say we have this circuit, right? This circuit is not that bad. Only has 1 resistor, 2 sources. Or how about let me try another one. This is a, how about this one? Well, 1 source and then 2 resistors. And then let's see how complex it is. Oh man, that's a video. I want to see some problem with that. Hopefully it won't lead to any crazy page. This one.
I can locate one on my own, but I was just wondering if it was going to be covered on any of if there's going to be questions on the test.
Oh, no.
Okay, then I'm okay.
Okay.
Thank you so much.
You're welcome. The reason is Kirchhoff law, no, we don't have it because even a few years ago, like 6 years ago, that time I started teaching the course. And then one day the department chair, the former chair told me, no, don't cover too much about Kirchhoff law. That's just too much. And then from that time, I stopped covering this a lot.
Okay.
For us, we just need to know the KCL, right? Just all the current entering to the node equal to all the current leave the node. For Kirchhoff voltage law, for a closed circuit, the total voltage equal to 0. That's all. And for solving the circuit using KVL, KCL can be very complicated. such as here. We have a very simple circuit, and at the end we build 3 equations, and then now we need to know maybe how to solve system of equations. At the time I covered this, at the time 6 years ago, I realized I think no one, all the students in the class don't remember how to solve system of equations. 3 equations with 3 unknown and solve for them. It's just crazy using KVL, KCL.
That's how I feel too. Thank you.
You're welcome. So the simple answer, no, we don't have this in the test. We don't have this on the homework either. But make sure you know KVL, KCL, the meaning of them. The concept is easy. And then to use them to solve circuit is pretty tedious. Any questions? Other questions? For the members have no questions, I think we can stop the meeting here today. And for the questions, for members have questions, please stay. If you're curious about how did you do in the test 1, and you're curious about the answer, I can show it to you. But I prefer to keep the answer offline. But if anyone want to know the answer for the test or which question didn't do right, please stay, and I can maybe we can meet in the breakout room. So only us I can show you, and the other members can wait, and I can show one by one, one-on-one also. Okay, so let me let's see. Anyone have questions? The first one, anyone can ask question. The first member ask the question, I help you with the first. Bernardina, do you have questions? Or Edward, questions?
Just one question that I had sent to you, and it was regarding a grade. I took a picture and I sent that to you. It's regarding assignment. Let me see, where is that assignment?
So first, let me